Hello everyone, I am Bharat Singla and welcome to our channel Learn Competitive Programming with CodeChef. If you desperately want to master competitive programming and get your hands dirty in data structures and algorithms, then this is a one-stop destination for you. Every week, we upload problem explanations from CodeChef's contests. We also upload conceptual videos on various programming paradigms and conduct live problem solving sessions. Yes, live interactive sessions. So before we begin, here's a reminder for you to hit that subscribe button if you haven't yet already. Great! Now that you have subscribed, let's get started. In this video, we will be discussing the problem Unusual Queries from CodeChef's November Challenge 2020. The difficulty level is going to be hard and the prerequisites for the problem are segment trees. And note that we are not using something like persistent segment trees or segment trees with lazy propagation. We are just going to use plain segment tree implementation that will contain the build function as well as the query function. Next, greater element is the second prerequisite for the problem, and you should know how to find the next greater element for each element in an array using stacks in O of n instead of O of n square, which is the brute force solution. So these are the prerequisites for the problem, and now let us discuss today's agenda. So first, we are going to, as usual, do the explanation of the problem statement. Then we are going to understand the concept required to solve the problem. And finally, we are going to do a quick summary as well as the walkthrough of the implementation. So let us get started. But before we begin, do you guys know that CodeChef also conducts free live sessions on Unacademy where we try to teach every possible topic related to competitive programming? We have list of courses for all skill levels, such as beginner courses like Introduction to Programming in C++ and Java, intermediate courses like courses on recursion, number theory, basic data structures, etc., as well as advanced courses on topics like dynamic programming, graph theory, segment trees, and many more. Here, you will be taught by top coding experts who are IUI medalists, ICPC World finalists, and have worked at companies like Google, Facebook, Flipkart, LinkedIn, and basically all those tech giants. All you have to do is download the Unacademy app or register yourself at unacademy.com by clicking this button Start Learning here and choosing your goal as competitive programming. But this isn't just it, guys. You can also go for the plus subscription where you get additional benefits as well as full time doubt solving and individual support. You also get the access to solve the problem sets curated by these top coding experts for each topic. And to add the icing to the cake, the mentors who are going to resolve all your queries are 6-star and 7-star coders as well. So subscribe to Unacademy Plus. Don't miss this golden opportunity of learning from the best in the world and kickstart your competitive programming journey today. You can also use the code Bharat27 and get an instant 10% discount on your subscription. So don't forget to use the code and hurry up guys, subscribe to Unacademy Plus. So here we are with the problem statement, guys. So in Chefland, there are n mountains where each mountain has an height associated with it and the mountains are arranged in a line. So you can say that if this is the heights array H, so these are the heights of the mountains, right? So now Chef visits these mountains in a very peculiar order. So you can say that if L and R we are given are 2 and 7, so these are the two bounds that we will be given in each query. So let's say we took L equal to 2 and R equal to 7. So this will basically be the bounds. So let's say chef starts from this mountain 5. So the mountains he's going to visit are 5 and then he's going to ignore 2 because it is less than his record, that was 5. So he'll not visit 2. Then he'll not visit 5 as well. For 3 also is not going to visit. But for 7, he will visit this mountain. Why? Because it was greater than his record. And once he has visited 7, his new record is 7. So he'll also not visit 2 as well. So now we can also define this variable satisfaction. So the satisfaction chef gets from visiting these mountains is equal to the number of mountains he visits. So in this case, he had visited 2 mountains, so the satisfaction was 2. He gets this satisfaction, right, if he visits this mountains, and it is equal to the number of mountains he visits. So in this case, he visited 2 mountains, so the satisfaction was 2. Now for each query, when we are given this L and R, what we have to do is find small l and small r, basically restricting him even more, such that, so if this is one bound, so we are bounding him even more, such that if he starts from this mountain here and goes on visiting every mountain of greater height, and not simply just visiting random mountains, he's going in this order. So he'll not basically skip any mountain, he has to visit a mountain if it is of greater height. So if he starts from this small l and he can go up till r, the satisfaction should be the maximum possible. So there are many ways we could construct these bounds. So the problem basically is that we should find these two bounds such that he gets the maximum satisfaction, and we have to print out the satisfaction for each query. So one very clear observation that we can make is that small r should always be equal to capital R. Basically, there is no point restricting him from the right. It's always beneficial to let chef go until the end. Now why? Because there is a chance that he visits the last mountain as well, or the second last mountain as well. So why restrict his range? Let him go up till the end that we are allowed. So till capital R, and there's basically it does not make any sense to cut down some mountains from the right. Let him go till the end so that we could maximize his satisfaction. Now there could be a case like here, if we visit 7, then he's not going to visit 2. So here instead of 2, we could have also taken 7. Both of them give the same satisfaction, right? But still, there's no loss in taking small r equal to capital R. Here, it could be something like 10. So if there was 10, so we could have visited another mountain and his satisfaction would have become 3, right? So it is always beneficial to take small r equal to capital R, right? And for small l equal to capital L, is this true? Is it always beneficial to take small l equal to capital L? No, it is basically not necessary. Now again, let's take up an example. So in this case, if he starts from 5, that is basically we take small l equal to capital L. What is the satisfaction he is getting? It was 2, that's what we have basically just seen right now. But what if? What if he starts from 2 instead? That is basically L plus 1. So think about the satisfaction that he'll get. So here the satisfaction he gets would be first he is going to visit 2, then he'll visit 5, then he'll ignore this mountain 3, again he's going to visit 7 and he'll ignore 2. So what was the satisfaction he got this time? It was equal to 3. So basically what I was trying to prove from this point was that there's no point always taking small l equal to capital L. There could be a case where this is beneficial, but it is not always correct. Like the first point, small r equal to capital R is always beneficial, but small l equal to capital L is not necessarily. Like here, if we take small l equal to capital L, that is, if he starts from the first mountain itself, he gets a satisfaction of 2. But if he starts from the second mountain, he gets a satisfaction of 3. So here we need to take care of small l. So the problem now basically boils down to finding where chef starts. So if we find where chef starts, and this is when we are taking small r equal to capital R. So basically we do not need to find the right bound, we only need to find the left bound. So basically where he is starting from. And in that case, what's the maximum satisfaction he can get? So here I have taken another array of heights that was 4, 2, 3, 1, 5, 5. Fine. So now this was a prerequisite to the problem for finding the next greater element for each element in O of n, right? Instead of O of n square, which was the brute force solution. So first is to find the next greater element. Fine. So here I am not going how we are building this array. This is a very standard algorithm, and you can always find this kind of algorithms on websites like Geeks for Geeks or Stack Overflow or anywhere on the net. So next greater, what actually next greater will look like, I'm going to explain that now. How we are building this in O of n using stacks, that was a prerequisite, so I won't be explaining that in a lot of detail. So here, if I just punch down these indices, so we are starting from 1 based indexing. So 1, 2, 3, 4, 5, 6. So if these are the indices for these heights, so what next greater will contain is for each element the smallest j, that is if we start traversing to the right. So if whenever we encounter an element greater than it, so the index will be stored at that position. So for 4, which is the next greater element, it is 5, its index is 5. So we are going to store 5 here. For 2, the next greater is 3 and its index is 3. For 3, the next greater is 5. So again, 5 will be the ng of 3 will basically be 5. For 1, again it is 5 and its index is 5. So in this case, 5 does not have any greater element in its side. So what we can do now is that we could add infinity here and then its index will be 7. So whenever we are unable to find an element, it always has to be less than infinity. So here we can store 7 because then infinity is the next greater element for 5. And 7 also denotes that we could not find any next greater element. So this is how the next greater array would look like. So before we proceed, let us make another array go forward where go forward of I, so go forward of I denotes the satisfaction the chef gets if chef starts at the ith position and he can go up till the end. So what the go forward array would look like is something like this. So for 4, what is the satisfaction he'll get if he goes up till the end? It is basically he'll visit 4, then he is going to visit 5, so the satisfaction will be 2. For 2, the satisfaction he gets will be 2, 3 and 5. So 3 mountains that he visited. So satisfaction is 3. For 3, the satisfaction he gets is 2 again. For 1, the satisfaction is 2 again. And for 5, the satisfaction is 1. We are only visiting the mountain 5 in both the cases. Now note that for one I, so go forward of I has to be distinct. That is basically if he starts at the ith mountain and since chef follows a very specific pattern, so there has to be only one satisfaction that he gets from one I. So we don't need to consider the max satisfaction. There only be one satisfaction for one I. So go forward of I has to be distinct and we do not need to take care of the max satisfaction. There will only be one satisfaction for one go forward of I. So this is how the go forward array looks like. So now the problem basically arises that how do we find go forward efficiently? So as compared to the brute force solution that takes n square. But during the course of the entire problem, we can never afford an n square algorithm. Why? Because n could be as large as 10 to power 5 and then 10 to power 5 square is 10 to power 10, which is way beyond the constraint. We can only perform around 10 to power 8 operations in 1 second. So 10 to power 10 is basically 100 seconds algorithm. So we cannot afford any n square algorithm. We have to get at max n O of n or n log n. So how do we find go forward array very efficiently? So what we can do is that notice that if he starts at this position, so if he starts at the fourth position, what is the satisfaction that he can get? So the satisfaction basically for every element is the satisfaction. So if he starts at this position, the satisfaction for here would be the satisfaction of its next greater element plus 1. Why? Because he is not going to visit any mountain between the element itself and its next greater element, right? It's going to visit in increasing order. So whenever it encounters its next greater element, he is going to visit that. So satisfaction of I, we can say that go forward of I is basically the go forward of next greater of I plus 1 because he is visiting this mountain as well. So how can we compute go forward of I? We can compute it this way. So go forward of I is equal to the go forward of the next greater of I. So go forward of next greater of I and this plus 1. Why plus 1? Because we are visiting the this mountain as well, right? So this is how we can compute go forward very quickly and very efficiently, and you can take this very similar to dynamic programming, right? Because instead of defining this go forward function, we are making this go forward array using some other values of go forward, so you can connect to dynamic programming as well. So go forward of I can be very efficiently computed using go forward of next greater of I plus 1. So initially we could assign some values like for the last mountain, the satisfaction, if we start from there and go up till the end, has to be 1. And then we can start traversing to the left and then assign this mathematical formula for go forward of I. Fine. So this is an O of n algorithm. So this is very fast. So now the key observation that was required to solve the problem. So this is basically the crux of the problem now. So the answer, so the satisfaction he gets from L to R, here he's starting at L and he can go up till R. So this is equal to go forward of L minus go forward of Jm plus 1. Now, what is Jm? First, let's define that as well. So, Jm for each L and R will be the index of the maximum element. So, let's say I take this heights array again and I take L to be, let's say, 2 and R to be 4. So, what is Jm for this case? So, Jm here, Jm is equal to the index of the max element from heights of L to R, both inclusive. So in this range L to R, what's the maximum element? It is 3. And what's the index of 3 if we are talking about one based indexing? It is again 3. So Jm in this case will be equal to 3. So now that we have found Jm, how is Jm applicable to this problem? Now note that once chef visits a mountain Jm, then he is not going to visit any mountain in this ride. So he is never going to go beyond Jm if he starts from something less than Jm or Jm itself. So you can take this like he is visiting this mountain and then he's going to visit JM. So JM will surely be visited if he starts from something that is less than or equal to JM. So if his start is less than or equal to JM, he will always visit JM and then he is never going to go beyond JM. Why? Because JM is the maximum element and he is only visiting mountains of increasing heights. So he is never going to go beyond JM. If this is JM, so he will never visit one, right? So now, how is this formula applicable and why is this correct? That is, the satisfaction he gets from L to R is equal to go forward L minus go forward Jm plus 1. Now you can take it very similar to the prefix sum technique, that how do you compute the sum from the range L to R? So you do this by computing the sum from L to end minus the sum from R to end, and you subtract these two values, right? So that is how you get the value for one range. So you take this value, then you take this value, and once you subtract this from this, you get the value for this range, right? And this is what very similar to what we are doing here as well. Go forward of L denotes the satisfaction if we start from L till the end. And what does go forward of JM include? Go forward of JM will basically tell us the satisfaction we are getting from 3 till the end, right? So what is the satisfaction we are getting from 2 to 3? We can subtract these two values and then we can add 1 because we are visiting JM as well. So if we subtract the smaller range from the larger range, we get this part of the query, right? And note that we are never going to visit this mountain. So subtracting go forward of JM is beneficial because we are never going to visit this mountain. So this formula is correct. Now you can also verify this. We had built go forward here. So what was go forward of L? If we take L equal to 2 and R equal to 4, what was go forward of L? That was go forward of 2, that was 3. So he's getting a satisfaction if he starts from 2 and goes up till the end. Yes, that's right, right? If he's visiting 2, then he's visiting 3, then he's visiting 5. So he has visited 3 mountains and his satisfaction was 3. And what was go forward of JM? Go forward of JM was basically go forward of 3, that was 2. So if he's visiting 2 mountains, that is 3 and then 5. So if we subtract 3 minus 2, go forward of L minus go forward of JM. So 3 minus 2 is 1, and that is correct. He is only visiting this mountain and that plus 1 because he is also visiting JM. So yes, we are getting 3 minus 2 plus 1, which is equal to 2, and that is the number of mountains he can visit from L to R. Yes, you can confirm that he is going to visit 2, then 3, and then he is not going to visit 1. So the key observation here was basically that after he visits JM, he is not going to go beyond that. So we basically don't need to consider this part of the segment that was left after JM. So from JM plus 1 to R, we do not need to consider anyways if we are starting from something less than or equal to JM. So now let's move on to the second part. So how can we find the answer? So the answer from capital L to R is basically we have to choose this starting point small l. So the answer from L to R is basically the maximum satisfaction that he can get from, so satisfaction of L to R, then satisfaction from L plus 1 to R, so on till satisfaction of JM to R. And let me also add this condition that L is less than or equal to start, which is less than or equal to JM. So if we are starting from something that is less than or equal to JM, then the answer for this query that we were getting for L2R was the maximum of the satisfaction we can get if we start from L and go up to R. Then the satisfaction if we start from L plus 1, then L plus 2, and so on till the satisfaction we get from JM to R, right? And this answer of L to R is basically the answer to the query if we are starting from something less than or equal to JM. Fine. So now let us mathematically deduce even more. So now note that this minus go forward of jm plus 1 is common for all these basically these formulas, right? We are calculating go forward of L, then go forward of L is different for all of them, right? Here it is go forward of capital L, here it is go forward of capital L plus 1, so until go forward of JM. But this part is common, minus go forward JM plus 1 is common. So what we can do is we can take it out from this expression and we can write it to something like this. So answer from L to R, capital L to R is equal to the max of go forward of L and go forward of L plus 1, so on till go forward of Jm minus, so here I am closing this max bracket and minus go forward of and then plus 1. So basically here I have not done anything very complex. What I have just done is taken out this part minus go forward Jm plus 1 since it was common for all of them. And now what we can do is that note that again this type of a query to get maximum from one range can be very efficiently done using a segment tree. So segment tree was the prerequisite, so I won't be going how a segment tree works and how we query it and how we build it. But here go forward of L, then go forward of L plus 1, so until go forward of JM to find their maximum we can use a segment tree. And now for each query, basically if there are q queries of this form, so the complexity comes out to be q log n because the complexity to query is log n and for each query q, the complexity will come out to be q times log n. So here we could use a segment tree so that we can get this maximum of this range of go forward from L to JM. Fine. But now one major point arises that what if we take the start to be greater than JM. Till now what we were doing is that we were starting from something less than jm, and that's why we were able to subtract this range, right? If we are starting from the left of jm, then only we can subtract this small range of jm. We can only subtract basically a small part from a larger part, right? But what if we start from something like 1 which was on the right of jm, so from jm plus 1 to r, if we start from that point, so we cannot subtract go forward jm, right? So go forward array does not work now. So what we have to do is let us make another array. So go back. This will be very similar to go forward, where go back of I denotes maximum satisfaction if we start from anywhere in the left but we end up at I. So this is very similar to the go forward array where we were taking the satisfaction we are getting if we start from I and we can go up till the end. Here we are talking about if we can start from anywhere but we end at I. So you can say this to be the opposite of the go forward array. Now I have rewritten these heights, and what the go back array for this heights for these heights would look like is that it would be something like this. So go back array would be this. For 4, what is the maximum satisfaction we can get if we are ending up at 4? That has to be 1, right? So go back of 0 basically has to be 1 in all the cases. For 2, what is the max satisfaction we can get? It is again 1. For 3, the max satisfaction is again 1 if we are ending up at that position, right? For 1, it is again 1 because if we are ending up at 1, we basically have not visited any mountain in its left because 1 is smaller than them, right? But for 5, what's the maximum satisfaction we can get? Now note that this is now contradicting to the go forward array, right? Go forward array basically only had one satisfaction for one I, but here we can get maximum satisfaction if we are ending up at 5. One way could be that we are starting from 4 and then we are ending up at 5. The other way could be we are starting from 2, then we are visiting 3, then 5. And another way could be if you are starting from 1 then visiting 5, right? So there are many ways we could end up at 5. So what will be the satisfaction? It will be the maximum all of all the ways we can reach here. So for 5, you may notice that the maximum satisfaction we can get if we start from 2 here. So if we start from 2, we get 2, then 3, then 5. So the satisfaction is 3. Now for 5 also the satisfaction is 3, right? So how can we again, now the problem is the same. How can we compute go back very efficiently in something like n or n log n? Because we can never afford something like n square or n cube, right? The problem does basically restricts us from using any kind of an algorithm which has that high complexity. So we have to build this go back very efficiently. Now again, how can we do that? So let's say we have these mountains, right? I'm just making some random mountains, and what the arrow denotes is that the tail of the arrow denotes that for this element, and the head of the arrow denotes its next greater element. So for this element, the next greater is this. For this also, the next greater is this. For this, let's say the next greater is this. So how can we compute go back? Now note that if we are ending up at this position, then we must have started from some element whose next greater was this element, right? So if we are ending up here, so we must have come from some mountain like this or this, right? So if we are ending up at here, we must have come from this whose next greater was this element, or this element whose next greater was this element. So we must have come from these two mountains only. If we are ending up at this mountain, so we must have come from this mountain, right? So again, we have come up with this smart recurrence relation, and not exactly recurrence relation. We can again apply kind of a dynamic programming, not exactly, but you can say that go back, go back of I. So go back of I is equal to the maximum of go back of j for all j, right? For all j. So for all j whose or such that next greater of j is equal to I. And finally this plus 1. So we'll also had to add 1 to it, right? So now this should be very clear that, so for this element, let's say we are taking this element. So for this mountain, if he's ending up at this mountain, he must have come from this or this. So if we know the go back of this element, that is we are ending up here and we are ending up here, so we can take the maximum and then we can add 1 because we are visiting this mountain as well. So go back of I can be calculated like max of the go back of j for all j such that next greater of j is equal to I. Now again, this can be computed very efficiently, and even if you are writing if you do not want to write a separate line for computing go back, or if it is getting very difficult, so what you can do is that when we were computing the next greater, that is when we were building that stack, and while stack is not empty and all that, so you can include this line there. So basically you have you know that for which elements the next greater was for j was I. So at that point you know it very clearly because you are building the next greater. So you can include this line there in that function when you are computing the next greater array. Fine. So this is how we can compute this go back array. And now how it is helping us is that the answer. So let me use a different pen. So the answer again from L to R, but this time jm plus 1. So we are is less than or equal to our start, and which is less than or equal to R. So this time we are not starting from L to JM. We are going from JM plus 1 to R, right? So here, if this is the start, so what will be the answer? It will be the maximum of go back of JM plus 1, and then go back of JM plus 2, so on till the go back of R. Fine. So now I want you to brainstorm about why we are not subtracting any values from this go back array like we did for the go forward array. Remember, for go forward, when we found the max, we subtracted go forward of jm and then added 1 to it. But here, why are we not subtracting any value from this max value, right? We should be subtracting ideally because go back is not telling us from JM, it is telling us from the start. So why are we not subtracting a value? I want you to, if you want, you can pause the video here and brainstorm about it. So this, the answer for this question is that if we are ending up at an element which is greater than JM, and yes, we are making a query only for JM plus 1 to R. So basically, if since this was the array here, the heights array, so if I take L equal to 2 and R equal to 4, right? So I basically making a query to only this element in this case because there's only one element to the right of JM, which was this element. So here, if I'm ending up at this position, so I have definitely not come from something that was less than JM. Had I come to this mountain from this mountain, then I must have visited 3 as well, right? Because it is in the increasing order, right? JM is the highest mountain, so we are definitely visiting JM if I am coming to this mountain from something which is left to the JM. So if I'm coming from this mountain, I must have visited JM, and that's why after visiting JM, I am never going to go beyond JM. So from JM plus 1 to R, I am never going to end up there. But in this case, we are ending up here, right? So this basically tells us that the go back array is taking care of itself. If we are ending up here, then we are starting from something as well that is after JM, right? So if we are ending here, we must have started from something that was to the right of JM. So go back array is taking care of itself and we do not need to subtract any values because anyways we are only starting after JM and we are ending after JM. So that's correct. Because again, let me repeat myself. So if we are starting, if we are ending up at this mountain and we have come from mountain which was less than JM or equal to JM, then in that case we are never going beyond JM. We are visiting JM, and since the heights are less than JM, so we are never going to go beyond JM. So from JM plus 1 to R. But since we are ending up here, that is what go back denotes. We are ending up here. So what this basically tells us is that we are also starting from somewhere in this range. So if we are ending up here or here, we are also starting from something that is after JM. So go back array is taking care of itself and we do not need to subtract any values. Fine. Now again, this can be a segment tree query. We are finding the maximum of an array from the range JM plus 1 to R. Fine. And yes, we have completely solved the problem except for the implementation. We have figured out the logic that if okay, if I take this to be answer 2, so this was answer 2, right? When we are starting after jm plus 1, and let me label this as answer 1 when we are starting between l and jm. So these are the two answers, answer 1 and answer 2. And how can we get the answer for a query? So now we have come to the solution, right? We have finished the problem and the answer for the query, final answer for the query. So final answer for the query L to R is equal to the maximum of answer 1 and answer 2. And here we go, we have this solution, right? So for final answer of L to R, either we are starting from something which is less than JM or equal to JM. In that case, we can use the go forward array, right? And subtract go forward L minus go forward JM and then add go forward JM plus 1. Fine. So this is how we are computing answer 1, and for answer 2, that is this answer 2 here, we are finding the maximum of the go back array, right, from gm plus 1 to r. Then this is again a segment tree query, so this will be done in log n, right? So for each query, the maximum complexity we can get is log n in both cases. And pre-computing next greater and go forward and go backward, so they are O of n, and that is when that has been pre-computed, right? So that is not the complexity of those building up those arrays is not included in a query. We are here only taking care of the, for each query we are only making two segmentary queries, right? And both of them are log n, so the complexity here comes out to be log n for each query. And for q queries, the complexity is q log n, which is fine, right? Q log n works as per the constraints. So here we go, we have the answer. And before moving on to the code, let us first discuss the summary. So now let us summarize or recapitulate what we have done above. So the first was to compute the next greater array. Fine, the next greater array. And what the next greater array is, it looks something like this. So it is 5 3 5 5 6 6. And what's the complexity of this algorithm? So here the complexity is O of n, right? Now for second, the second step was to compute go forward as well as go back. Again, the complexity for this was O of n for both of them. So O of n plus O of n is equal to 2 times O of n, which is equal to O of n again. And these are how the go forward and go back array look like for these given heights. Remember that. Now the third point was to build the segment trees so that we could make the queries and build the segment trees on which arrays. We are going to build the segment tree on the heights array so that we could get JM again and again, the maximum index in the range L to R. We are also going to build an segment tree on the go forward array so that we could get maximum of L to JM again and again, right, in log n, and also on go back. Fine. So again now to find the maximum of go back from gm plus 1 to r again and again very efficiently using segment trees. It will be a simple segment tree query, right? So the first was to build the next greater array. The second was to compute go forward and go back using this next greater array. And you can write a separate block of code for this go forward array. But the code for the go back array can be inculcated into this next greater array when we are building that stack so that we know for which element the next greater is I. Fine. And the second part was to build the segment trees so that we could use the max query again and again. Then the fourth step was to, for each query, now we are talking about each query. These were pre-computations after we were given the heights array. These three were built just after we were given the heights array, and there were two more inputs that were the number of queries and S as well, because we need to compute the L and R for each query online, right? We are not directly given the input. Basically, we have to use a mathematical formula to come to the L and R we are given from X and Y. But for now, for each query, now we are talking about each query here. So from the fourth step, we are talking about each query. So fourth step is to find JM, and this will be a segment tree query on H, on the tree of H. Now what the fifth step will be is to find answer 1, which is equal to the maximum of go forward. Now this will be a segment tree query, guys. Now why segment tree query? Because we want to find it in log n instead of O of n. So this will be answer 1 will be equal to the max of go forward from L, capital L, to JM, right? And this minus go forward of JM, and that plus 1. Fine. So this is what the answer 1 variable looks like. Now the sixth step will be to compute answer 2. Now this is very similar to the first one. This time we are computing the maximum, again a segment tree query on the tree of go back. So go back of JM plus 1 to R. Fine. And here we don't need to subtract or add anything. This is what we have discussed above, right? Why we don't need to subtract. So these are answer 1 and answer 2. And finally the answer. So let me just choose a different pen here. So the seventh point will be to print maximum of answer 1 and answer 2. Fine. So here we go, guys. We have discussed the full explanation, and this will fetch us 100 points. Now, one thing to take care is that answer 2 will only be computed if JM does not equal to R, right? Because then JM plus 1 to R basically makes no sense. If in case JM is equal to R, that is the index of the maximum element, turns out to be the rightmost element. So in that case, we don't need to compute answer 2. So it will basically be a simple if check. If JM is less than R, only then we are going to compute answer 2. Fine. So finally we are printing out the maximum of answer 1 and answer 2, and this is going to fetch us 100 points. So let us do a quick walkthrough of the implementation, and the code is going to be in C++, guys. So first we are going to initialize a few variables like n, the length of the input array, heights array, the next greater, the go back, the go forward, as well as an index array. Then we are going to initialize arrays that will basically be the segment trees. For tree of GM, that will be a segment tree on the heights array, which will give the index of the maximum value in the range L to R. Fine. Then also a segment tree on the go forward array as well as on the go back array, so that we can constantly and continuously make max queries in log n. Fine. Then we are just going to define this very kind of a common segmentary function that will build this tree, as well as a query function that will basically return what we function we pass in. In most cases, it's going to be the max function. Fine. Then we also define this function get jm. It is again going to return us jm by making a segmentary query on the heights array. Fine. Then get max forward, again a segmentary query on go forward of L, then go forward L plus 1, so on till go forward R. And get max back, again a segmentary query to find the maximum of go back of L, so on till go back of R, basically in the range L to R. Fine. Now we come into the main function where we define variables q and s. We have already defined the variable n above. Now we are going to take the input. Fine. Then we are going to initialize the go back as well as the next greater array. In this block of code, we are doing two main things. First is that we are using stacks to compute the next greater array for each I from 1 to n in O of n. Fine, this is a very standard algorithm. But what we are also doing is that here in this line, we are also computing this go back array. Fine, that is what I mentioned in the explanation as well. We can calculate go back array since we want the next greater element for all elements, and this is done in the stack. So we can insert this line here instead of making another block of code which calculates go back. So here we have inserted this line, and this is going to find the go back array as well as the next greater array. Then here we are computing the go forward array and now building a segment tree for GM. That is basically a segment tree on the array heights. Fine. Then we are going to again build a segment tree on go forward as well as on go back. Now we come to the main part where we are initially taking answer is equal to 0, and then while q minus minus, basically for each query we take into inputs x and y. Fine. Now L, basically we are L and R we are defining using this mathematical equation. This was given in the problem statement as well. We are processing these queries online. We are computing L and R from X and Y that are given. And if L is greater than R, we are swapping them. Fine. Now one main point is that we know that answer has to be at least 1. So we can initialize answer is equal to 1 and int gm is equal to get gm from L to R. Again a segmentary query on the array heights. Then we are going to update the answer considering all the intervals within L to gm. So answer 1 or answer is equal to the max of answer. That is for the first query. The first query answer was 1. So this is basically for the first query it is max of 1 comma get max forward L and gm, a segmentary query, minus go forward gm plus 1. This is exactly what we discussed in the explanation. So there's no rocket science going on here. Then we are going to make a check that if jm is less than r, because there was a possibility that jm could be equal to r. So in that case we cannot make a query like from jm plus 1 to r. That will basically go out of bounds. So we have to make this if condition first. Then we are again going to set answer is equal to the max of what the answer currently is, as well as a segmentary query from jm plus 1 to r on the array go back. Finally we are going to print the answer, and this is how the implementation goes. Now let us try to submit the code as well. I have already pasted it on the submit tab, and now let's hit this button and hope for an AC. So yes, we have got an AC, and this was it for the implementation.